Alrighty, everybody. This is a little introduction to the nature of light. And the reason it's so important to talk about the nature of light uh, in astronomy is because light is really the only tangible thing we get from things in space, with the exception of the moon rocks brought back by the astronauts back in the 1970s and late 60s, and with the exception of meteorites that fall to Earth randomly. We really don't have any material from space that we can analyze like other scientists do. Geologists can collect rocks, biologists can collect biological samples, things like that. We also can't do controlled experiments in a laboratory. You can't drag a star into a laboratory or a planet into a laboratory. So light is all we've got to go on. So to understand how we figure out clues in astronomy, we have to understand something about the nature of light. The first thing to understand about light is that it is energy. Light is a form of energy, and it's a form of energy that has no mass. And also when we talk about light, we're not just talking about the light we can see with our eyes. We are talking about various other types of light that together make up what we call the electromagnetic spectrum. Okay, and that includes a lot of types of radiation that we're very, very familiar with. For example, radio waves are basically the same thing as light, except our eyes cannot see radio waves. We use radio waves to transmit sound and to transmit pictures over and your cell phone, texts and things like that. Those are all carried by radio waves. Shorter wave radio waves are sometimes called microwaves. They can be used for communication, but they can also be used to cook things. So we often think of microwaves like in microwave ovens. Infrared, sometimes we call infrared light heat radiation because our skin is very good at detecting infrared radiation, and it feels warm to us, feels hot to us. But there's no real difference between infrared light and the visible light we see, except that our eyes cannot detect it. Then we come to visible light, and you're probably familiar with the sequence of letters, Roy G. Biv. That's the colors of the rainbow, the colors of the spectrum: red, orange, yellow, green, blue, indigo, and violet. Infrared is beyond the red part of the spectrum, and then if you go beyond the violet part of the visible spectrum, we get ultraviolet. Okay, so ultraviolet is past the violet. If you go farther and farther into the ultraviolet spectrum, we get what we sometimes call X-rays. Okay, and if you go even beyond X-rays in the spectrum, you get an even higher energy form of radiation, which usually only comes out of nuclear decay and things like that. Those are called gamma rays. Now, as you can see, there's some of these things are called waves and some of them are called rays, and there's a reason for that, which we'll get to in a moment. But also notice that on one side of the visible spectrum, you have types of radiation that are fairly harmless. Okay, radio waves, microwaves, and infrared generally don't hurt you very much unless you have them at extremely high intensity. So we'll just say that these are mostly harmless. Okay, and there's a reason for that we'll get to in a moment. On the other hand, you should probably try to avoid ultraviolet radiation as much as possible. Ultraviolet kills stuff. It can be damaging to your cells. Oftentimes it is used to sterilize food because it kills microorganisms. X-rays can be very useful, but you should minimize your exposure to X-rays because it could also damage your cells and cause cancer. And gamma rays are something that should be avoided at all costs. So these guys here are dangerous. Okay, these are dangerous and are to be avoided. Now, all of light has wave properties, and all of light also has properties of like particles flying through space. It's harder to tell the wave property of X-rays and gamma rays because it turns out they have very, very short wavelengths, and therefore the wave properties are kind of hidden. Whereas radio waves and microwaves and all the way to visible, their wavelengths are more substantial, and we can see the wave properties more easily. Okay. So light, electromagnetic radiation, does have properties of both a wave and a particle. And And you might wonder, well, what's doing the waving? What's waving? Because light, unlike waves in water or sound waves, for example, that needs some air or something to transmit the sound, light waves can go right through empty space. And basically, light is a pattern of electric and magnetic fields. Okay, so light is a pattern of these oscillating magnetic and electric fields transverse to each other. In fact, they are called transverse waves because they oscillate perpendicular to the direction of motion. So, for example, in this figure, you've got waves that are oscillating perpendicular to the direction of motion, which is to the right. And the direction of motion is also the speed of the wave. And that's extremely fast. The speed of electromagnetic radiation is the speed of light, which is the fastest speed of anything that can travel in the universe. Okay. Now, how do we know that light is a wave? Well, because it exhibits properties of a wave, properties of typical mechanical waves like waves in water, things like that. Okay. One of the properties it exhibits is called interference. If you plunk two stones into a pond, it'll make circular waves. If you plunk them down at the same time, those circular waves will move out away from the rocks like this. And there are places where the wave crests are going to meet other wave crests, and the effects will add up, and you'll get higher wave crests. But there are other places where the wave crests from this one is going to meet the wave troughs from another one. And when that happens, you get them canceling out. Okay? You get cancellation of the waves when they're completely out of unison, when the wave crests from one wave is meeting the wave trough from another, the two waves cancel out completely. On the other hand, when they're synchronized, when you get the wave crests meeting other wave crests, you get higher waves, okay, and you get an enhancement of the wave. Now, if these were sound waves, you would get very, very loud sound here, and then you would get very little sound or no sound here. In fact, this is how noise-canceling headphones work. What they do is there's a little microphone in the headphones that takes in the sound and inverts it and turns the crests into troughs and the troughs into crests and mixes it with the sound from the outside to cancel out the sound completely. So basically you're canceling out sound with the inverted wave of the sound that's coming in. This can also be seen with light. If you shine a light through two slits, there are going to be places where the waves from one slit are synchronized with the waves from the other. So the crests are meeting the crests here, and the troughs are meeting the troughs here, and you get a bright patch. On the other hand, right in between, you're going to get a dark patch. The dark patch is where the wave from one hole, the crest from one hole is meeting the trough from the other, and vice versa. So you get cancellation here. And again, this is kind of like noise-canceling headphones. You would get an absence of light in these places, just like you would get an absence of sound with the noise-canceling headphones. Okay. Another property that light exhibits is polarization. Okay, because light is a transverse wave, like the wiggly waves of a string or a rope, like this. You get light oscillating either up and down or side to side, depending on the polarization. So, for example, if you could take a garden hose or a string and wiggle it up and down through these fence posts, if the fence posts were aligned, it would just go right through. On the other hand, if you have fence posts that are transverse to each other, if you wiggle your string up and down like this, and then you make your fence post side to side like this, it will not get through both. We can actually see this with polarizing material. If you ever had polarized sunglasses, the polarized sunglasses are doing pretty much just the opposite of this. In polarizing sunglasses, what you have is you want to get rid of glare. Glare happens when light reflects off a horizontal surface. So the light is oscillating side to side, kind of like this. Okay? And the polarizing sunglasses have these little molecular slits So it's kind of like a picket fence that's aligned vertically. So if you put that in the way, then it gets rid of all the side-to-side light and only lets through the vertical light. And so it gets rid of the glare. It gets rid of the light that's shining off of the flat surface. Okay, and so you could see inside the water, for example, that otherwise you wouldn't be able to with the glare. Or if you're driving along a road and there's glare in your eyes and you're having trouble seeing, you put your polarizing sunglasses on and the glare goes away. It doesn't get completely dark, but at least the glare tends to go away. Okay. All right, so some of the properties of waves. The wavelength is the distance between wave troughs or wave crests. Light has a very, very short wavelength, although it's nowhere near the shortest wavelength there is. Light has wavelengths between 400 and 700 nanometers. Okay, it means that you could fit about 2,000 wavelengths of light in a millimeter. Okay, that tiniest division on a ruler, you could fit 2,000 wavelengths in just that little tiny space. Frequency is another property of light. Frequency is how many wave crests are passing by in a certain period of time. Okay, the frequency is related to the wavelength because light travels at a very high speed. So the more that the waves are bunched together, the higher the frequency is going to be, and the more they're spread apart, the lower the frequency is going to be. Okay, the units of frequency are hertz. Okay, a hertz is a number of waves per second. So if you were like sitting on a fishing pier watching the waves roll in and you counted how many come in per minute, that would be a kind of a frequency. So if it was 6 waves per minute, that would be the frequency of the waves. Well, generally what we do is we measure them in waves per second. So if you have an old radio that has an AM and an FM dial on it, you'll see that the FM is in megahertz, which is in millions of waves per second, and the AM is in kilohertz, which is in thousands of waves per second. That just tells you the carrier frequency of those particular radio stations, which are carrying the signal. And by the way, let's not get radio waves confused with sound. Radio waves are not sound. They sometimes carry signals that are then translated into sound, but the radio waves themselves are not sound. Okay, it's not the same thing. Okay. Well, if you saw a bunch of waves coming in and you knew how far apart they were spaced, you could figure out the speed, right? Because if, say, 6 waves come per minute and each of those waves is separated by, say, 1 meter, that means that the speed of the waves would be 6 meters per minute because you got 6 of them, each separated by a meter, so they're traveling at 6 meters per minute. In the case of light, the speed is always the speed of light, so that's very, very fast. Okay, the speed of light is 300,000 kilometers per second, or 3 times 10 to the 8th meters per second. That's the fastest speed there is, but just like all waves, the speed of the wave is equal to frequency times the wavelength. Okay, and the important thing there is that means that if you, because the speed of light has to stay the same, okay, the speed of light always stays the same. That means that if you were to stretch out the wavelength, if you were to increase the wavelength, the frequency would decrease. Okay. On the other hand, if you were to decrease the wavelength, the frequency would increase. Okay. So what this is saying is that frequency and wavelength are inversely proportional. Frequency is inversely proportional to wavelength, and wavelength is inversely proportional to frequency. Okay. So the wavelength of light, wavelength and frequency of light are inversely related. When you have a long stretched out wave, you have low frequency. When you have a short bunched up wave, you have high frequency. This is very similar to what you would get on a rowboat. If you have choppy waves that are close together, you would be bouncing up and down very quickly. When you have long stretched out waves, you would be bouncing up and down with very, very low frequency.